So in this example, the equivalent circuit model analysis, I want us to assess our knowledge on torque relations. So we have a 480 volts, 60 hertz, 6-pole, 3-phase, delta connected induction motor, which has the following parameters. So you're given the parameters and you're told to determine the following. One, the Thevenin equivalent parameters and the Thevenin voltage. And based on that, you will calculate the pull-out slip, pull-out torque, and the starting torque. So I'll give us a minute or two to think through the question, refresh your mind, and then based on the equivalent circuit model of the IEEE induction motor, we are going to derive this and calculate this. So let's solve the question together. So first of all, if we recall, we said that for purposes of deriving the torque relations, it was easier to Thevenize the starter side of the circuit. So we viewed the starter from this point of view, and we Thevenized this circuit. If you recall Thevenin's theorem, when we are Thevenizing, we get the voltage as will be viewed from this point, and that will be the open circuit voltage. And then if you look at the impedances, it seemingly looks that XM is parallel to the impedance of the starter. So that's what we do in our solution. So the first thing is to calculate the Thevenin impedance as the impedance of the starter parallel to the XM, and we get the expression. And then the voltage will be the open circuit voltage, or we can use also voltage divide rule to get the voltage across XM. And that is the expression. So if we substitute the parameters given, since we have been given XM, X1, and so on, we can be able to get all these values. And consequently, V Thevenin expressed in absolute values is this, and R Thevenin and X Thevenin. So that's the first part of the question, to be able to calculate this. Now, there is a part 2 of the question, and part of it is in form of an assignment to use Scilab. For now, we limit ourselves to Scilab to plot the torque speed curve for the slip in range 0 to 1. Torque speed curve for slip in range 0 to 1. So based on this part of the equation, we can now determine part 2. Part 2 was the pull-out slip, the slip at which maximum torque occurs. So, and that we can use the maximum power transfer theorem. And if you recall, maximum transfer theorem, if I would go back to our circuit, the equivalent Thevenized circuit, for maximum power to be transferred here, the value of this impedance must be equal to the internal resistance of the rest of the circuit, as viewed from the 2 points where the load is. So based on that, we can equate R2 over S to be equals to the Thevenized part plus X2. And from there, we can be able to express S as the subject of the formula, and we get the pull-out slip to be 0.276. So all the slip at which maximum torque occurs. Then pull-out torque, or the maximum torque. So first of all, we need to get the torque. If we recall from our notes, the torque was given as 3 times the Thevenin voltage squared over the impedance, or put in absolute values is R Thevenin plus R2 over S, and X Thevenin plus X2 squared. then multiplied by R2 over S, and then divided by the synchronous speed. Now, if we want to get the maximum torque, we can get it directly from here, or by substituting this equation by the slip. So we put the slip. So whichever case we can, we'll be able to get the maximum torque. Since we know the maximum, the slip at which maximum torque occurs, you can use directly this equation, or we use this equation, and we get 1942 Newton meters. And then finally, the starting torque. Again, same equation. We remember at startup, the slip is equals to 1. So we equate, we substitute for that in the slip is equals to 1. And when we substitute for all the other parameters, we get the starting torque for this particular machine is 1182. So part of your assignment is to be able to plot now this curve based on these equations that we have derived together. So that's the end of three-phase induction machines. The rest we will consider them in form of, the rest of the assignments we'll consider them in form of assignments in Scilab. Now we go to single-phase induction motors. Now single-phase induction motors are actually very similar to three-phase induction motors. It has a squirrel cage rotor, identical to that of the three-phase, but it has a single-phase winding in the starter, unlike the three-phase induction machine. And consequently, because it has a three-phase, a single-phase in the starter instead of a three-phase, that implies the single-phase induction motor is not self-starting and requires some mechanism to help it start. So this is a schematic diagram of how a single-phase induction motor would look like. So this is the squirrel cage rotor, and then we have the starter windings connected to a single-phase supply. Now, if the starter is connected to a single-phase supply, the starter winding produces a magnetic field that pulsates in strength in a sinusoidal manner. The field polarity reverses after every half cycle, but the field does not rotate. Consequently, the alternating flux cannot produce rotation in a stationary squirrel cage rotor. However, if it is possible by an external mean, auxiliary means, to start the motor, then the motor will quickly attain a final speed. So for us to be able to understand the concept of how the motor obtains a final speed after being started, it is necessary to understand the double field revolving theory. So if you recall, for the three-phase induction machine, we talked about the revolving magnetic theory in stationary windings. When we come to single-phase induction motors, we are now talking of double field revolving theory. So the principle of operation of the single-phase induction motor is much more complex than that of the three-phase counterpart. So for us to understand the double revolving theory, I want you to consider this diagram. So we are having a magnetic field. We're having a magnetic field revolving, alternating from zero to peak, and that is reflected by the cosine rule as indicated. So to better understand this, we are going to look at an animation shortly, but briefly, as the magnetic flux oscillates from alternates due to the alternating current, the magnetic field will increase and decrease, but will only be pulsating from 0 to peak, and then from 0 to negative peak. But there will be no, it will not be revolving as was the case of the single phase, of the three-phase induction machine. So to be able to understand that, let's consider this animation. So we have already said the external structure is the same. The internal structure of the rotor is very similar to that of this three-phase induction machine. However, the starter winding is single phase. So, and in a commercial machine, there's an auxiliary winding to help start the machine and a capacitor. We'll be talking about why we need the two. So this is the main winding, which is single phase, and has, since we know that current flows, whenever current flows in a conductor, there's a magnetic field. And since it's an alternating current, when it is flowing in the positive direction or in one direction, it creates a magnetic field revolving in one direction. And when it moves in the opposite direction, again, it creates a magnetic field in the opposite direction. So that's why we are seeing the current alternating, the magnetic field alternating from 0 to peak, but not revolving. So in essence, we have two magnetic fields. We can dissolve them into two magnetic fields. So the pulsating field produced by a single phase AC motor can be resolved into two components of half the magnitude rotating in opposite directions at the same synchronous speed. So if we allow FM to be the pulsating field, which has two components, each of magnitude phi m over 2, then both are rotating at the same angular speed omega radians, but in opposite directions, the resultant field will be phi m cos theta. Thus, the resultant field varies according to the cosine of the angle theta. And this, again, we understand further through this. So as the current moves from peak to negative peak, the flux in the starter will have a cosine shape. We'll also have a cosine shape. So, and if we, as we have mentioned, the flux can be divided into two. So one flux is rotating in anti-clockwise direction, and another flux is alternating in clockwise direction. And the total flux is viewed in this shape of a cosine rule. So the aspect of dividing the flux into two components is where the double revolving field revolving theory comes in. So again, we discuss the alternating flux produced by the starter winding can be represented by the two fluxes, phi 1 and phi 2, each equal to 1/2 of the maximum value of alternating flux, and each rotating at synchronous speed in opposite directions. So let us allow the flux phi 1 to rotate anti-clockwise direction and forward, which will be the forward direction. And then we allow the flux phi2 to rotate in the backward direction, which is a clockwise direction. The flux phi1 will result in the production of torque T1 in anti-clockwise direction, while the flux phi2 will result in the production of torque T2 in the clockwise direction. At standstill, these two torques are equal and opposite, and the net torque developed is zero. Therefore, the single-phase induction motor is not self-starting. So again, we view in form of an illustration. So what we are saying is that each of the fluxes phi1 and phi2 will result in torques T1 and T2. So torque T1 will tend to be in the anti-clockwise direction as suggested, and torque T2 will be in the clockwise direction. At startup, when the motor is about to start, both torque T1 and T2 are equal. Consequently, this machine cannot self-start. So it requires some mechanism of pushing it so as to move either to the left of the S1 or to the right of S1. For example, if we move to the left of S1, then torque T1 will be greater than torque T2 because this is the resultant torque. So that means we'll have a positive torque, and consequently that torque will be the one pushing the motor to move in the anti-clockwise direction. Again, if we say we push the motor to a slip greater than S1, then we will land at a negative torque outside beyond zero, and consequently the machine will rotate in the clockwise direction as guided by torque T2. So the work of the auxiliary winding and the capacitor is to help the machine move self-start by allocating the starting point either above S1 or below S1. So that's why we introduce the auxiliary winding and the capacitor. Now, rotor running. So we explain further. Assume that the rotor is started by spinning the rotor or by an auxiliary circuit, say in the clockwise direction. The flux rotating in the clockwise direction is the forward rotating flux, phi F. And the other direction is the backward rotating flux, phi B. So with respect to the slip, with respect to the forward flux will be the forward slip as the synchronous speed minus the motor speed over the synchronous speed. So this is known as the forward slip. And the slip with respect to the backward flux will now be SB will be N minus N over NS, or NS plus N over NS. And from here, we resolve and get it is 2 minus the forward slip, or generally S. So when we talk of single-phase induction machines, I mentioned the concept becomes a bit more complex because now we are talking of two fluxes revolving in opposite directions. We are talking of two slips, a forward slip and a backward slip. So in other words, finally, we'll be considering it as if there are two motors, one rotating in the forward direction and one rotating in the backward direction. So the forward rotating flux slip is usually less than unity, while the backward rotating flux is usually greater than unity. The torque at slips of less than unity are greater than those of slips of greater than unity. The resultant torque will be in the direction of rotation in the forward flux. Thus, if the motor is started, it will develop a net torque in the direction in which it has been started, and will function as a motor. So what we are saying is, without the auxiliary winding, without the capacitor, if you start this machine, it will just be vibrating, but not rotating. And the direction to which you will tip the rotor to rotate is the direction that that motor will develop net torque and start rotating. So the auxiliary windings are set such that they will cause that mechanism of rotating the machine in the direction required. So that's the purpose of the auxiliary windings and the starting capacitor. So because of the need to start the machine, then the next subtopic will be, how do we start single-phase induction machines? So there are different mechanisms, and you will notice all of them will be geared towards the same direction. So let's consider first the split-phase induction motor. So the start of the split-phase induction motor has two windings. It has the main winding and it has the auxiliary winding. And these windings are displaced by 90 electric degrees. And I believe you are aware there's a difference between mechanical degrees and electric degrees. And this is shown here. So this is the switch, and then we have the two windings, the main winding and the auxiliary winding. The auxiliary winding is made of thin wire so that it has a higher R to X ratio as compared to the main winding, which has a thick super enamel copper wire. When the two starter windings are energized from a single phase supply, the current IM and IA in the main and auxiliary winding lag behind the supply voltage, IA leading IM as shown. So if we have the supply voltage, both IA and IM, since they are inductive in nature, will lag behind the voltage. However, IA having a higher R to X ratio will lead IM having a lower R to XM ratio, and the resultant current is as shown. So this means that the current through the auxiliary winding reaches maximum first, and the MMF of flux due to IA lies along the axis of the auxiliary winding. And then after some time, the current IM reaches maximum value, and the MMF due to IM lies along the main winding. So now we have two fluxes, one leading the other. So this causes the motor to become a two-phase unbalanced motor. Because the two fields in the starter is developed, the motor becomes self-starting. So it already has a torque ahead of the other one. So it becomes self-starting. After the motor starts, the auxiliary winding is disconnected, usually by means of a centrifugal switch that operates at about 75% of the synchronous speed. Finally, the motor runs because of the main winding. Since this being a single phase, some form of humming noise is always associated with the motor during running. The rating of such motors is usually between 60 and 250 watts, so they are not very big. So the typical speed characteristic is as shown. So during startup, we have both the main and auxiliary winding at around 75% of synchronous speed. The auxiliary winding is switched off, and we now operate on the main winding. So characteristics, mainly due to low cost, the split phase induction motors are the most popular single phase induction motors in the market. Since the starting winding is made of thin wire, the current density is higher and the winding heats up quickly. If the starting period exceeds 5 seconds, the winding may burn out unless the motor is protected by a built-in thermal relay. This motor therefore is suitable where starting periods are not frequent. So then we have capacitor run induction motors. So concept remains the same. We want to introduce two phases to the machine. However, we want to smoothen the process, so a capacitor is introduced to improve the starting and the running performance. So the capacitor start motor is identical again to the split phase, with the exception that the starter winding has as many turns as the main winding. Moreover, a capacitor is connected in series with the starting winding as shown. So the value of the capacitor is chosen such that IA again leads IM, but now not by a small angle, but by about 90 degrees, so that the starting torque is maximum for certain values of IM and IA. Again, the starting winding is opened by a centrifugal switch when the motor attains 75% of the synchronous speed. The motor then operates as a single-phase induction motor and continues to accelerate until it reaches the normal speed. So again, this is the phasor diagram. So in this case, the capacitor is selected such that IA and IM are almost at 90 degrees. And again, due to the capacitor, IA now will be leading the voltage. So the typical curve, you can see now there's a great improvement. So the starting torque is high, and then immediately after startup, we can now operate. The switching off can happen, and we operate using the main winding. So although the starting characteristics are better than those of the split phase motor, both machines possess the same running characteristics because the main windings are identical. The phase angle between the two currents is about 90 degrees compared to about 25 degrees for the split phase motor. Consequently, for the same starting torque, the current in the starting winding is only half that in the split phase winding. Therefore, the starting winding of a capacitor start motor heats up less quickly and is well suited for applications involving either frequent or prolonged starting periods. Capacitor start motors are used where high starting torque is required and where high starting period may be long to drive. For example, compressors, large farms, fans, pumps, and high inertia loads. And then we can see there's an improvement. So such motors range between 120 watts to 750 watts. Then we have still another type, the permanent split capacitor motor. Concept remains the same. In this motor, the capacitor that is connected in series with the auxiliary winding is not cut out after starting and is left in the circuit all the time. So in this case, we do not remove the capacitor. This simplifies the construction and decreases the cost because the centrifugal switch is not needed. The power factor, the torque pulsation, and efficiency are also improved because the motor runs as a two-phase motor, and the motor will run more quietly. The capacitor value is of order 20 to 50 microfarads because it operates continuously, and it is an AC paper oil type. The capacitor is a compromise between best starting and best running. Therefore, the starting torque for this type of motor is sacrificed. So we have a lower starting torque. If you recall, the static torque as a percentage when we removed the capacitor was almost to 300, but this one now is at 50. The motor is the characteristic. The motors are used where the required static torque is lower, such as air moving equipment, fans, blowers, and so on. Now we have capacitor start, capacitor run kind of starting of induction motors. So in this case, we have two capacitors, one for starting and one for running. So again, if you think about it, we now want to combine the aspect of having a higher starting torque by switching off one and having a smoother run by retaining another. So that's the capacitor run, capacitor start, capacitor run kind of induction motor. Theoretically, optimum starting and running performance can be achieved by having two capacitors. So the starting capacitor is larger in value and is of the AC electrolytic type. The running capacitor permanently connected in series with the starting winding is of smaller value and is of the paper oil type. Typical values of these capacitors for 0.5 horsepower induction motor are about the starting one 300 microfarads, the running one 40 microfarads. So again, the typical curve we can see now there is a great improvement. We have the starting torque greatly improved, and the other advantages of having a running capacitor are also maintained. So the characteristic generally are ability to start heavy loads, extremely quiet in operation, high efficiency and power factor, ability to develop 25% of overload capacity. Hence, such motors are ideally suited where load requirements are severe, as in the cases of compressors, conveyors. Currently, we have them in the fridge and washing machines. Then we have a different concept, what we call the shaded pole induction motor. So these motors have a salient pole construction, a shaded band consisting of short-circuited copper tan, shown as a shading coil is used on one portion of each pole as indicated. So we have a shading side and on this side. So when the alternating current flow through in the field winding, an alternating flux is produced in the field core. A portion of this flux links in the shading coil, which behaves as a short-circuited secondary transformer. A voltage is induced in the shaded coil, and this voltage circulates a current in it. The induced current produces a flux called the induced flux, which opposes the main core flux. The shading coil thus causes the flux in the shaded portion to lag behind the flux in the unshaded portion of the motor. So due to this, we have a displacement between the two fluxes, the main flux and the shaded pole flux. And the displacement is slightly less than 90%. Since there is time and space displacement between the two fluxes, again, we end up having a two-pole machine. And these are the conditions necessary for setting a rotating magnetic field. Under the action of the rotating flux, a starting torque is developed on the squirrel cage rotor, and the direction of this rotating flux is from the unshaded to the shaded. And typical characteristic is as indicated. So this is also a method of starting. So the characteristic, so one is that this is an extremely simple construction and there is absence of centrifugal switch. Since starting torque efficiency and power factor are very low, these motors are only suitable for low power applications like small fans, toys, and air dryers. So rating is only up to 30 watts. Good. So equivalent circuit of this single phase induction motor. When the single when the starter of the single-phase induction motor is connected to a single-phase supply, we already said that the starter produces a pulsating flux. So according again to the double revolving field theory, the pulsating air gap flux in the motor at standstill can be resolved to two equal and opposite fluxes in the motor. Since the magnitude of each of the flux is a half of the alternating flux, it is convenient to assume two rotating flux acting on two separate rotors. Thus, the single-phase induction motor can be considered as consisting of two motors having a common starter winding and two imaginary rotors which rotate in opposite directions. At standstill, the impedance of each rotor referred to the main starter winding is R2 over 2 and plus JX2 over 2. And thus the equivalent circuit would look like this. So we have the starter, and then we have the forward rotating imaginary rotor, and then we have the backward rotating imaginary rotor. This is at standstill, or before we start rotating. So now suppose that the motor is started with the help of an auxiliary winding, and the auxiliary winding is switched out after the motor gains its normal speed. The effective rotor resistance of an induction motor depends on the slip. The slip with respect to the forward rotating flux is S, and the slip with respect to the backward rotating flux is 2 minus S. So when the backward and forward slips are taken into account, the resultant equivalent circuit will be as indicated. So again, the forward slip will be 2S. In the backward slip will be 2 in brackets 2 minus S. So consequently, this machine will revolve in the forward slip direction. So the impedance, the rotor impedance representing the effect of the forward field referred to the starter winding is given as ZF is equals to, as the equation is represented. So where this is parallel to this or equivalent to this. Similarly, the rotor impedance representing the effect of the backward field referred to the starter winding, M will also be given as ZB equals to this, or this parallel to this, and we get the equation for ZB. So we had ZF and ZB. So the simplified equivalent circuit of a single-phase induction motor with only one main winding energized is given as this. So this is important to note, especially the last statement, with only one main winding energized. So this case assumes that the auxiliary winding is going to be switched off upon the machine obtaining 75% of the synchronous speed. The current will thus be the total voltage divided by the total impedance. So we now bring in the starter impedance. Then the air gap power will be again composed of two. We'll have the forward air gap power and the backward air gap power, where the forward air gap power will be related to RF, the forward resistance, and the backward air gap power will be related to the backward resistance RB. So the difference between the two air gap powers will be the resultant air gap power for that machine. And then the torque produced in the forward field will be given as this. The torque produced by the backward field will be given by this, and consequently the induced torque will be the difference between the forward torque and the backward torque. Or we can say the induced torque will also be PAG over this, or 1 over the forward air gap power minus the back air gap power, or IM squared over the synchronous speed, RF minus RB. Again, the copper losses will now be treated differently because it's a sum of all the losses, both the forward and the backward. But we can also calculate them as follows. The total losses will be the slip multiplied by the air gap power. So the slip in the forward direction is S multiplied by the air gap in power in the forward direction, and the backward slip is 2 minus S multiplied by the backward air gap power. From there, we can calculate the mechanical torque to be developed or availed as given as this, or 1 minus S, the synchronous speed multiplied by the induced torque, or given by this, or the mechanical power can also be given by this equation. And finally, the shaft output power will be mechanical power subtracted by all the mechanical losses, which constitute of core losses, mechanical losses, which sometimes are called friction losses, and stray losses. So with that, we'll consider this example next time, but you can go through it and also attend to the assignment as uploaded in the portal.